Good day everyone and welcome to the presentation for our MOSITIS project. Our subject of choice for this project is modeling, simulating and optimizing of active and passive countermeasures for earthquakes in order to avoid excessive damage to structures. To solve this task, we first set out to create a model of the building on which we wanted to carry out our tests. A lumped parameter model was constructed for a structure of n floors in which all the mass is concentrated on the floors and all the damping and stiffness is concentrated as a damper and a spring element between the floors, as can be seen in the bottom figure. Where an earthquake occurs, the ground will accelerate and this will cause the structure to vibrate. The bond graph for a building of n floors is shown on the right and was implemented in Simulink. The first countermeasure that will be tested is a passive control system called the base isolation system, and the idea is illustrated in the figure on the right. The n-floor building is shown on a moving cart that represents the base, which is coupled to the foundation by an element which behaves according to the Book-Wen model and is held in place by shear keys. The adapted bond graph is shown in the lower left corner and includes the Book-Wen hysteresis model. The idea is that, when there is no earthquake, the shear keys are engaged and the base is rigidly coupled to the foundation. The building behaves just like any other building. When an earthquake is detected, the shear keys disengage and the base is able to move relative to its foundation. This movement is dictated by the Book-Wen model. This way, only part of the vibrations caused by the quake is transmitted to the superstructure.
Next to passive control, active control is another option to achieve vibrational damping of the building structure. More specifically, we chose a hybrid damper actuator bracing control system, as can be seen in the figure on the slide, where a K-brace is installed on the first floor and a hydraulic actuator and fluid damper are installed in the upper floor. We chose this system because it combines the reliability of the passive devices with the adaptability of the active control devices. The motion equations for the servo-valve controlled hydraulic actuator, viscous fluid damper and the K-brace are defined in the slides, where beta, A, V, KV, PS, tau are parameters defining the hydraulic actuator, which are given by the manufacturer, and lambda 0 and C0 are the relaxation time factor and the damping coefficient at zero frequency for the viscous fluid damper, which are also defined by the manufacturer. Now that we have the motion equations for the hydraulic actuator, the viscous fluid damper and the K-brace, we can easily implement these for a general structure consisting of n floors and m hybrid damper actuator bracing control systems. We'll denote these equations in the state space formulation because we will need the state vector z of t, the plant matrix A, and the coefficient matrix for the control commands BU in a later chapter where we'll design the optimal control for this system. Due to the existence of the actuator and damper dynamics, we must include the degrees of freedom of the actuator and the damper in the state variables. So we define the state vector z of t with state variables x of t, x dot of t, fa of t, fp of t, and c of t, with order capital N, where capital N is defined as 2 times n plus 5 times m. This is because there are n plus m elements in either x of t and x dot of t, and m elements in either fa of t, c of t, and fp of t. So we now obtain the state variable representation of the hybrid structural control system as defined in the slides.
Because the cost of placing an HDAB system is quite large, the amount of control devices in one building will be limited. The placement of these control devices will have to be optimized. This optimization will be done using the genetic algorithm. Herefore, a certain cost function is needed. This will be the maximum displacement of all floors. To get this displacement, a certain form of control is needed. This will be the optimal control. For the optimal control input, the objective function j will be minimized. To get the gain matrix in the feedback law, the Riccati equation will have to be solved to find R. For this genetic algorithm, the building will be represented by a binary string. Each floor represented by a bit, 1 meaning there is a control device on the floor, 0 meaning there is no control device. The problem with general genetic algorithm lies in the fact that there is a fixed amount of control devices. This constraint won't automatically be satisfied with normal crossover procedure. The identification crossover protocol seen in the figure on the slide will be used. This ensures each offspring has the same amount of control devices as its parents. As mutation, a bit swap will be used. Firstly, the parameters of this genetic algorithm are tuned using a test function. After all the right parameters were found, a real test was done using the El Centro earthquake. After 9 iterations, the optimal placement was found. This is seen on the slide. The figure shows the average cost and the best cost. You can see that after 9 iterations, these are the same, and thus the procedure will be terminated.
Now that the optimal placement of the 3 hybrid vibration control systems is known, a controller can be designed to steer the actuators and then the vibration of the building as such. In order to do so, first an overview of the inputs and outputs of the plant and controller is given. The output we want to minimize by reference tracking is the displacement of the 10th floor. The displacement is influenced by the generated actuator forces on the one hand and the earthquake forces on the other hand, which are modeled as a measured disturbance. The plant output is sent back to the controller via feedback, as well as the earthquake force. The latter is done such that the controller can generate appropriate signals for the actuators, taking the disturbance coming from the earthquake into account. In order to ensure that the actuator forces evolve to 0 after the earthquake, targets equal to 0 are set for the actuator forces. Once we have an idea about the controller inputs and outputs, the tuning of the MPC can be done. This consists of choosing a suitable set of design parameters, which are the sample time, prediction horizon, control horizon, constraints on input and output, and weights that indicate the relative importance of the controller goals. It is important to note that general guidelines exist to determine the design parameters, but nevertheless, trial and error are mostly involved. Following this strategy, a controller can be designed leading to the results shown in the figures. At the bottom left, the displacement of the scaled 10-story building subjected to the El Centro earthquake is shown with and without MPC. The maximum displacement is reduced with almost 50%, and the displacement in general is significantly reduced. At the right side, the corresponding actuator forces are shown. To remark similar behavior of the actuators, they generate forces in the order of kilonewton according to a decaying pattern. It isn't clear from the scaling of the axis, but also note that the second actuator generates higher forces in the order of 10 kilonewton.